we consider a pair MG, which is geodesically complete to the Riemannian manifold or spacetime in general relativity. We suppose that there is Lorentzian signature metric and denote coordinates by x alpha. If Greek letters run from the beginning of alphabet, then they run from 0 to 3. If we take indices from the middle of Greek alphabet, then they run only space indices 1, 2, 3. There is a theorem. Let for the dimensional spacetime be the topological product of real line R times S, where t belongs to real line is a time coordinate and x belongs to S, is a three-dimensional space of constant curvature. We suppose that sufficiently smooth, homogeneous and isotropic metric of Lorentzian signature is given on it. Then there is such coordinate system in some neighborhood of each point where metric has the form. It is written here, where a of t is an arbitrary function which is called scale factor, and g hat denotes negative definite three-dimensional constant curvature metric on S, which depends only on space coordinate. This theorem is very important in cosmology because in fact it lies in the foundation of almost any cosmological model. Short history. First, this metric was introduced by Friedman in 1922. He didn't formulate the theorem and didn't prove it. He simply used this metric to describe, to construct cosmological model. Later, Lemaitre used also this metric in several cosmological models. He didn't formulate the theorem and he didn't prove it. Robertson wrote several papers. In the first two papers, the theorem was formulated, but it was not proved. Instead, Robertson referred to the paper by Hilbert by 1924 and Fubini by 1904 instead of the proof. In the third paper, metric 1 was obtained in a different way by considering a set of observers with given properties. Tolman also wrote several papers approximately at that time, and metric 1 was obtained from different assumptions. In particular, he assumed spherical symmetry and used Einstein equations. Walker also wrote a paper, and in his paper the theorem was proved in one way, namely he proved that the metric which was given on previous slide is homogeneous and isotropic. So in the original papers there is no proof of this theorem at all. Usually it is usually said that Friedman was the first who used this metric, but Robertson and Walker rigorously proved the theorem from group theoretical point of view. And this is not the case. The proof is absent in their papers. Moreover, there is no definition what is homogeneous and isotropic universe, because intuitively the definition is very clear, but mathematically it is not clear at all. In general relativity, space-time is a manifold, and there is no vector structure on this manifold, and therefore there are no translations and rotations. So the proof of the theorem is not difficult. The most difficult point is to give definition of homogeneous and isotropic universe. The first mathematically acceptable proof is given in the book by Weinberg, Gravitation and Cosmology, as far as I know. Let me briefly discuss constant curvature manifolds. We have let k hat be a Gaussian curvature. It can take three values, minus, 1, 0, and 1. If you choose spherical coordinates on S, constant curvature space, then the three-dimensional part of the metric takes one of these three forms. And in this form, there is nothing to be generalized. But let us consider space part of the metric in stereographic coordinates. There is the explicit form of the metric. Constant B0 is related to Gaussian curvature by a simple formula. If Gaussian curvature equals to 1, then X runs over whole R3 Euclidean space. The same is for k equals 0. But for negative curvature spaces, X runs, takes values inside the ball. So this is the metric in stereographic coordinates. Now let us make a coordinate transformation, which depends on time through function through the scale factor a of time. Then metric takes off-diagonal term form. And now we simply drop off-diagonal terms and put G00 to 1. Then we get this metric. It depends on two arbitrary functions of time. A is the usual scale factor, but here enters B. B is an arbitrary, sufficiently smooth function of time, and it cannot be removed by coordinate transformation. So, at first sight, this is a generalization of the Friedman metric because it contains two arbitrary, not one, but two arbitrary functions of time, and they cannot be removed. And why this metric is interesting? Suppose you have a solution of Einstein equations where B goes through 0. It means that topology of space will change during the evolution of our system. Therefore, it seems to be interesting. We do not know such solutions at the moment. Let us consider Einstein equations. Let us take energy momentum tensor as homogeneous and isotropic second rank tensor. Then mixed components of Ricci tensor are proportional to B dot, time derivative of function B, and due to Einstein equations, B must be constant. And we return back to Friedman metric. I skip the proof. Of the theorem because I have no time. And the answer is the following. This metric is not homogeneous and isotropic. Also, every section of constant time is a constant curvature space, but as a whole, the metric is not homogeneous and isotropic. The space Killing equations are satisfied by this metric, but the mixed Killing equations are not satisfied. I didn't show this, but it can be easily checked. For this metric, Killing vector fields in stereographic coordinates do depend on time. And this contradicts homogeneity and isotropy. You can also compute scalar curvature, four-dimensional scalar curvature, and you will see that scalar curvature explicitly depends on space coordinates. And this is forbidden for homogeneous and isotropic scalar. Let me repeat the theorem in different words. The space-time, let space-time be the topological product of real line times constant curvature three-dimensional manifold. Let it be homogeneous and isotropic. Then, up to coordinate transformation, the most general metric is where G mu is the metric of constant curvature on S, and A of t is a scale factor. In this coordinate system, the Killing vector fields do not depend on time. And this is an important statement. And now I give, as far as I know, a new definition of homogeneous and isotropic spacetime. Spacetime M, which is a topological product, is called homogeneous and isotropic if every section of constant time is a three-dimensional space of constant curvature. And the second requirement, extrinsic curvature of a submanifold is homogeneous and isotropic. This requirement is necessary because I gave a counterexample. It is not sufficient that every section of constant time is a three-dimensional space of constant curvature. The second requirement is necessary. In our notation, extrinsic curvature for block diagonal metric is simply the time derivative of space metric. Okay, thank you. Everybody knows.
Okay, that's it, Mikhail.